Okay, so 2 days away from dang midterm, which I just finished writing the real one. Today's all about making sure that you are as ready as possible. Since we have plenty of time for that. Anyone have any questions about the practice? And
Is the main test going to be like very similar to that?
in terms of the types of questions, yes. So what would change would be like the particulars, like what kind of series, or sequence. But as far as the things that you are asked to do, that it's very similar. Are any of those problems anyone would like for me to talk about?
Number 10.
For 10? Okay. Okay, we have this series. To infinity. -1 to n. Over n. Natural log. And I start n equal to 2 because at n equals 1, natural log of 1 is 0. So it would be undefined. So is it so the three possibilities? It could be divergent. It could be absolutely convergent. Or conditionally convergent. And which is it? Okay, so what you can do is try picking from one of the various choices of convergence tests to apply to this. And which would be a logical choice to determine whether it converges at all or not. Even forgetting about absolute versus conditional, we'll deal with that later. What would be an appropriate test to apply to this series?
Alternating series test.
Alternating series test, that sign flipping is your tip off there. So the alternating series tests, what you do is you check the rest of the expression, so you ignore the sign flipping. 1 over n natural log of n. And for that, it has to be decreasing. And it has to go to 0 as n goes to infinity. And here you can rely on your knowledge of certain simpler functions being increasing. So the denominator, n natural log of n, is increasing. And I'm not going to require you to actually go to the trouble of proving it. And you can always try proving it by taking a derivative and seeing it as positive. No, I'm not expecting you to do that. Because certain functions like n to a power or natural log of n or some number b raised to the n power, an exponential function, if b is greater than 1. All of these you can take for granted. Oh, this here, p must be positive. All of those you can take for granted are increasing functions. So n and natural log of n, both are increasing. You multiply them together, that's still going to be increasing. 1 over that, therefore, will be decreasing. And because the denominator just keeps getting larger and larger, okay, so I could say something more. Not only are they increasing, they all go to infinity as n goes to infinity at different rates, but they do. So for that reason, you include that 1 over n log n is also going to go to 0. So because the expression you're summing up, if you set aside the sign flipping part, once you establish it is increasing, it's going to 0. Therefore, at least you know it converges. So this possibility is out. What you don't know yet is whether that convergence is absolute or conditional. And we're going to take a look at that. But first, I want to see if there's any questions about what just happened here. If you know that a series converges, but you don't know whether it's absolute or conditional, how do you check that? By what? Yeah, you take the absolute value of the terms. So does this series, we take the absolute value of -1 to the n, or n log n, which is just going to be the series down from 2 to infinity of 1 over n log n. Does that converge? Okay, if so, then you know that it is absolutely convergent, otherwise it'll be conditional. So now we're focusing on this series right here. So you go to your inventory of tests and pick one of those out and use that to check whether it converges, and which is a good choice here. Not what I would have picked, but it doesn't mean it doesn't work. You know what? It's
Yeah, I was thinking ratio too.
I was thinking integral test.
Integral test, because you see what happened. Ratio. Okay? What can you tell me what happened if you do try ratio test? What you would get?
Bunch of funky like n+1s going everywhere.
Yeah.
That wouldn't really help.
Yeah. You take the limit of that ratio, you're going to get 1. In that case, therefore, ratio test will be inconclusive. All right, integral test. So you try to evaluate the integral. Okay, so from 2 to infinity, because the series goes 2 to infinity, 1 over x natural log of x dx. How would you evaluate an integral like that?
Substitution.
Yeah, substitution. Okay, what's a good substitution? Natural log of x. And the way you can tell is you have 1 over x sitting there, which is a derivative of natural log of x. And this is what I'm going to talk about when I teach Cal 2, which hasn't happened in forever. But anyway, it's a good idea to set u equal to some portion of your integrand if a derivative of that portion is right there. So du is 1 over x dx. Okay, so then you end up with 1 over u du, and the new limits would be from ln to infinity. All right, so then you carry out the integration, but what happens is this function goes to infinity as u goes to infinity. So value is integral, it's actually going to be infinity. So the integral diverges. So that's the underlying series also diverges. So what's the conclusion? Yeah, so because this series diverges, final verdict is that it is conditionally convergent, because the original series you were given does converge. But once you take the absolute value of the terms, that series does not. So it's conditional. Yeah.
But it's like, I think I'm just confused in the algebra of how to get it down so I can cross things out.
Okay. The algebra.
Like, I guess I'll show you, but it's a geometric series. I wrote them down right here.
Oh, there's a different problem, or?
Yeah, it's in a geometric series, but I just get confused on how to get it to where it is used.
Oh, okay. Wait, something went wrong, something. Are you from here to here?
No, these are separate problems.
Oh, okay.
Yeah.
All right, so, actually, okay, well, first, we'll talk about that in a second.
Okay.
Do you have any questions about this problem? Right. Eraser. Oh, okay, thanks. Why did they hide that? Okay. All right, how about you pick one of those that seem particularly vexing and just tell me what it is.
Okay. Let's do, I guess, this one. So 2 raised to the n over 8 raised to the 2n plus 1.
Okay.
Oh, n equals 0.
Okay. All right, and so I guess the problem is to see if it converges or not.
Well, it's, yeah, and then enter the sum of the series. If it
Okay,
works.
yeah, and because we have numbers raised to the n power or something related to n, you can see this is going to be a geometric series, so you will be able to figure out the sum if it converges. So you'd like to get this in the form n equals 0 to infinity a r to the n for some r and some a. So if you have an expression like this one, the 8 to the 2n plus 1, where your exponent is not n, but some function of n, then you want to use the laws of exponents to write it in the form of something raised to the n. And if it means you have to take some of it out and set it aside, then that's what you do. So what you can do with this, I'm going to leave a 2 to the n the way it is. And then I'll write the 8 to the 2n plus 1 as 8 to the 1 times 8 to the 2n. So if you have sums in your exponent, break them up. Then, so now we're going to have a 1/8 that's written separately. And then 8 to the 2n, you can write that as 8 squared to the n. So another law of exponents, we can break up a exponent that's a product. Now you have numerator, denominator, both raised to the nth power. Now you can rewrite that by having one fraction all raised to the n. And now the number that's inside is your r. The number that's sitting outside is your a. So by using laws of exponents, you can isolate that r. And then whatever other junk is sitting there, if it's independent of n, it's A. That's your A.
That makes sense.
But yeah, so this one definitely would converge. Any other particular practice test questions you want to examine?
You just go down the line. Sometimes it's better to have an explanation than to see an answer, you know?
Yeah,
Oh, actually, here's one I think everyone here would appreciate if we did.
okay,
So this is number 12.
Okay.
So it's compute a power series for the function f of x.
I got it here.
Yeah.
Yeah.
So number 12.
And actually, if no one else has anything, I was gonna talk about that one anyway. You'd argue that it's maybe this problem where you're given a function and asked to find a power series for it. Maybe the hardest one on the test. Okay, so first I'll step through this one and then I'll talk about some of the things that would come up and how you deal with them. Okay. Four over quantity 4 minus 6 squared. And then hint is that the derivative of this function, 1 over 4 minus x, is 1 over 4 minus x squared. So almost the same function, just missing an x. Okay. And the corresponding problem on a real test will also have some kind of hint that you'll definitely want to make use of.
I have a question.
yeah.
So I know you said, in your last lecture that, well, when last in-person lecture, that there'd be a series that like definition paper or something?
Oh, the book,
Yeah.
yeah.
So what would be included on that?
Yeah, is that?
Yeah. Yeah, so the last page of a practice test that has the list of convergence tests will be included with the real test.
I see, okay, cool. Now it's rolling at 8.
Okay. No, it will be included and then you just tear it off.
Okay,
But that way, because you have it, I mean, that's less things to try to memorize. Right. But still having practice applying those tests is good because you want to keep referring to that sheet every 5 seconds.
Yeah.
Okay. So the idea is to get a series for this function, you first get a series for this one. And then because you know a derivative of this, but it has you almost to your function. Once you have a series for this, you can take the derivative of this series term by term. Then you'll have a series for this function. And since the only difference between this function and this one is multiplying by x, you can take the series for this one. So you get this series second, then just multiply all the terms by x to get what you're really after. Okay. So, the first stage of this is start with the function that relates to a geometric series most closely. 1/4 minus x. But you want to write it in a form where it's easier to write down what the geometric series is. So you're using this formula that the sum n goes from 0 to infinity of a r to the n is a over 1 minus r. So you want to get this function to look like this, to fit this form. So that is the key to doing any of these kinds of problems. Get it in that geometric series form in whatever way you can. So what's the discrepancy between this and this that I need to deal with to make it look like this?
The four.
A 4 is a problem. I need a 1 there. All right, fine. So you multiply top and bottom by 1/4, and you'll get 1/4 up top, and then you'll have 1 minus x over 4 down below. But now it is in that form. So you can write the series for it. So it's going to be a sum n equals 0 to infinity of your numerator, that's your a.
Wait, can you talk through the last step that you just did one more time?
Oh, here.
Yeah, no, above, like there's that whole putting it together.
Okay. I need a 1 here.
Mhm.
So I got to divide top and bottom by 4.
Okay,
Whatever's there that's supposed to be a 1, divide top and bottom by it. Once you have that, whatever's sitting in the numerator is your a, and then whatever is subtracted from 1 down below, that's the r. So that is the series for this function, 1/4 minus x. Question so far? Okay, we got this one. Now we're going to go up to this function. So since 1/4 minus x quantity squared is a derivative of its function for which we do have a series, what is being done to the function is now done to the series. So here's a good way to look at it, since I'm just repeating the hint right now, 1/4 minus x, but I know the series for this, so I can substitute it in there. X over 4 the n. But you can see, maybe possible to rewrite this algebraically, but it might be better to avoid doing all that, like until you get to the end. All right. So now I'm just going to take the derivative of that term by term, and that just involves using a power rule. So I'm going to have a sum from 0 to infinity. All right, so I have 1/4, and then I have n times x over 4 to the n minus 1. Okay. Actually, by chain rule, I'd have another factor of 1/4 here. So this 1/4 just came along for a ride. This full 1/4 came from taking the derivative of what's inside here. Question is here. Actually, it's
I'm drawn, why did the 1/4 come for a ride?
already here, it's gonna come down.
Okay,
Um,
no, I know how the second one's there. I'm trying to figure out why the first one's there though. Why wouldn't it get,
constant multiple,
okay, is it constant stays, okay,
yeah, constant factor will stick around. Constant added will go away.
okay.
Yeah.
Oh, yeah, okay.
So then you did outside, inside to get that second one.
Yes, table, yeah.
Yeah, the
Yeah.
end comes from, yeah.
Okay. I can make it a little clean this up, it's getting a little cluttered. All right, so up top I have an n. And then I have x to the n minus 1. Down below I have a 4, another 4, and here I have 4 raised to the n minus 1 power. So I have n minus 1 plus 1 plus 1 again. That's going to be n plus 1. So I'm going to have 4 to the n plus 1.
Wait, one more time.
All right. So I have 4 to the first, 4 to the first,
Okay,
and then I have 4 to the n minus 1.
so
Add all the exponents together
I see.
to see how many 4s you got.
Okay,
Yeah.
that makes sense. So 1 plus n minus 1 plus 1.
Yes.
Yeah.
Okay. All right. Also, I've had this theory starting at n equals 0 the whole time, but I could also start at n equals 1 because this term will be 0 when n equals 0 anyway. Okay,
Okay.
and so other ways to equivalent, but
N.
so now we have a series for this function. Any questions about how we got that far? Now, we're so close to having a series for our original function. So as you're going from one step to another, it's good to write the function you're trying to get a series for in terms of a function you have a series for. What I mean in this case is this is just x. If I write it separately, like that, then you think, oh, well, this function, I have a series already. So you just replace it. Then you can take the x that's sitting outside and move it inside. N x to the n minus 1 times x. Or 4 to the n plus 1. But now you just your law of exponents thing. And get n x to the n. And now you're done with the main part of the problem of just finding the series.
Wait, pause.
Yeah.
I don't have a question, I'm writing. It's like group work.
Does anyone have any questions about this stage of it?
Would you explain again how you got n equals 1?
Okay, I could have left it at n equals 0, but if you look at what you have here, if I did start off at n equals 0, the first term would be 0. So I might as well toss it out.
So it doesn't matter.
So on this particular question, are you pretty generous with credit? Because there's a lot that can
Oh,
go
yeah.
wrong.
Yeah, okay. What I will do is if I first I'll look at your final answer. If
Okay,
your final answer is correct, great, full points. Well, if you show the work. If not, I'm gonna go through your whole process and see where did you go wrong,
okay,
and then assign partial credit based on that. The more you show me that you know something, then that makes it easy to justify giving you some points. And I appear to be a bit more generous than my colleagues about that, but I guess it's up to you, Judge. Yes.
So for some questions like number 3 on this one, you can just like look at it and kind of tell that it's like converging. You just want us to like, if it's something you can just tell from looking at it, you just want us to write like a little explanation and say. If you want to.
Yeah. Give me something,
Okay,
like not just an answer, but I mean, it could be a very brief explanation. You know,
it could
'cause,
be like it converted because of this rule.
yeah, like for example, that number 3 you're talking about, just so everyone can see.
wait, did we get the final answer for number 12?
No, we're not.
Well, this is part of the final answer. I'll go back to it.
Okay,
Where you give it a sequence, is it n over n log n over n squared plus 1? Well, it's about growth rates.
Mhm.
So, and you can cite that. And if I have some idea as to what you're thinking to arrive at the answer, and especially, I know this is a test with time pressure and all that, so you can be brief. You can abbreviate, whatever, as long as I can make sense of it, and I've had a lot of practice making sense of things that you people write. So,
I
then.
would hope spelling doesn't matter, but it's definitely not.
you'll get partial credit.
I will probably point it out, just because, I
Refer you to
can't
the
help
writing
it, but
center.
that, I would not take off points for it. Yes,
What's that side box thing?
oh, this is because there's a question on number 3.
Oh, okay.
Yeah,
So what is the answer?
well, the answer to this one, the question was whether it converts to,
Guys, we're still in number 12.
it goes to 0. As n goes to infinity, because the denominator grows faster.
Like really, I don't think it's gonna work like.
I mean, can you just like?
Yeah.
Uh,
We're good, okay. Let's
Yeah,
return
that's
to
what-
number 12
Thank you.
and finish number 12. All right. So this is the main part of the final answer, finding a series for a function. There's one part that remains, that is finding a radius of convergence.
Yeah.
So. And for that, you can use a ratio test. Right, so then you take the limits as n goes to infinity of, okay, so we have our expression here, with n replaced by n plus 1 throughout. So we have n plus 1, x to the n plus 1, over 4 to the n plus 2. Absolute value, and then this expression, but flipped. 4 to the n plus 1 over n x to the n. Now, the n plus 1 over n, that's just going to go to 1. So that's not going to affect anything. You have x to the n plus 1 over x to the n. That's to the x. And then you have 4 to the n plus 1 over 4 to the n plus 2. So actually, you just get x over 4 is what the limit turns out to be. Oh, okay. Actually, yeah, in the solution, I had not worked this out, I arrived to the radius of convergence a different way. And we want this to be less than 1 for convergence, but you have to rearrange it so its absolute value of x minus the center is less than something. The center in this case is 0. So that is your radius of convergence.
Do we have to do it like that, or could we rewrite the original, the series that we found to be geometric and then use the R as,
This series?
Yeah.
It's not geometric.
I guess because it's got the end on the outside?
Yes. Yeah,
Can you break down the, n+1 x into the plus, like, I understand how you got those things, but can you just like show a little bit more work to get to the x over 4?
Okay.
I'm sorry.
all right, so we have that,
Mm-hmm.
okay, then I have 4 to the n+1 over 4 to the n+2.
Mhm.
So then you get 1/4. And then x to the n+1 over x to the n, that simplifies to the x. But this goes to 1.
Okay.
That's why it doesn't appear here.
Okay.
And then everything that's left doesn't even depend on n. So that's why I dropped the limit.
So I have a question.
Yeah.
So this is, if you had to put like a definition on exactly what we did on 3, what would you say?
This right here.
Yeah.
Actually, I'll come to that
Okay.
separately, but like I should mention, in the solution, I wrote up a different way of getting the radius of convergence. Because here you have a geometric series. So this converges if and only if absolute value of x over 4 is less than 1, you get the same conclusion.
Yeah, that's what I was thinking, I just.
All right. But then you have to keep in mind that series is geometric, but nothing else here is geometric. How do the things that you do affect the radius of convergence? When you take a derivative of a power series, that does not change the radius of convergence. So the radius for this series, the first one, r was 4. Here we took the derivative, so r is still 4. And then when you're multiplying by a power of x, again, does not change the radius of convergence, so r remains 4.
But the interval changes.
The interval, and this question didn't ask about the interval, but the interval can change when you do those things. Yeah, so in general, differentiating, integrating power series or multiplying by a power of x minus the center does not change the radius. And yet, since the radius is particularly easy to get for a geometric series, if you want to, you can take that approach to get the radius, or you can wait until you're done finding a series and then do the ratio test. I don't care. Are any questions about, other questions about this specific problem?
Oh, we do all this work, but what we do is we circle our answer at the end, like the tool.
Yeah, don't make it too hard for me to find your final answer.
Okay, so our final answer is
Hey,
4.
if I have to do work, you'll have to do work too. Have it.
I have to grade 32 of these. What I did do, okay, I guess the only, aside from like minor change from content, in terms of formatting, what I did for the real test is for problems 11 and 12, I did a full page instead of half a page.
Let's do 2.
Okay.
Dude, might as well just go down the line.
I don't think we'll do.
Well, I have a
all
couple
the
questions about a homework,
Oh, okay.
but Mike can wait till after.
Okay, well, before I go to number 11, the last thing I want to say about this type of problem is transformations that might happen to operations on power series, some of which were shown in this problem. So if you have a power series, I'll just make a generic one. En x to the n. Okay. So, um, let's assume that the radius of the original series is 9. For example, maybe use a geometric series. Okay, so in other words, you're given this series, you're given its radius, and now you're going to do something to that series to change it. So the first thing you could do, which you saw in this problem, is term by term differentiation. That leaves you with sum from n going from 1 to infinity of n Cn x to the n minus 1. And the radius of convergence is still r. So like I said, it does not change the radius. Second thing we need to do, the equivalent test, is taking the antiderivative, so integrate term by term. So when you have Cn x to the n plus 1 over n plus 1. Don't forget the plus c. That's not added term by term, but there's a plus c added onto the end because we're taking an antiderivative. That too does not change the radius. A third thing you can do is you multiply by some power x to the p. So you get Cn x to the n plus p. That's the only change that gets made. And that too does not change radius of convergence. You just wonder why I'm talking about radius of convergence at all, because nothing seems to change it, except for the last thing.
Multiply.
What?
Going on for number 3, multiply by x to the t.
Yeah.
Okay.
Okay. All right. And then probably the most interesting change is you replace x with some constant, which I'll call b times x to the q. Trying to use all different letters for these things. So you make a substitution throughout. So your new series is going to be the coefficients you had before when you have bx to the q all raised to the nth power. That'd be the same as Cn b to the n x to the qn. And this change will affect the radius of convergence. Because before you had a requirement that absolute value of x must be less than r, whatever radius of convergence it had. But now when you make a substitution, the expression you're substituting must be less than r. But you have to rewrite this so that you have absolute value of x less than something. So if I just carry out the algebra here, then you divide both sides by absolute value of b, and then you raise both sides to the 1 over q power. Okay, so so this right here is the new radius of convergence, whenever you change like that. So that's an example. Suppose you're replacing x by x squared, whatever radius of convergence you had before. Now you got to take a square root of it. Um, So these are the kind of things, transformations that may have to be made to a power series to get it doing. So like you're starting with a geometric series, and then by doing any of these in combination, then you can cover various functions. Question about rules of the road here. Okay. All right, I'll do 11.
Yay.
I think you all have the most angst about power series.
Yeah.
Yeah.
So at least the only two power series problems will be thoroughly covered. And we'll see if there's time for anything else.
Can you, you already made your tabs, but please don't do number 4 dice. We change the regular. Or have you already done that? Have some mercy, man. We're coming up on Easter.
This covers a lot of possible changes. Some are simple as others. I'll have no further comment on the matter.
I didn't like that answer.
You did it.
Okay, I suggest you watch the video of my discussion of this,
Yeah.
and then you will be better off. Okay. Well, the other point I should make is, there's two ways you can go to figure out the rates of convergence. One is don't bother with it at all until you get to the very end, do the ratio test, like I showed when I worked out the problem. Or like I discussed in the solution for number 12, start with geometric series, figure out its radius, and then you figure out if anything you did to the series changes it. So, so you can use whichever approach you feel more comfortable with. Because if you're not sure, if you can keep track correctly of what happens with various transformations you make to a series, then just forget all that and do a ratio test at the end. So that won't steer you wrong. Okay, so this one is radius and interval. So number 11 asks about the interval convergence. Number 12 will not, only radius. 1 to infinity. N plus 1 n over n squared 2 to the n. Okay. So first, to get the radius, I'll use a ratio then. Generally, that's what you would use. The only exception I can think of is if the entire expression you're summing can be written as something raised to the n power. I can see you use a root test in that case, but since we have this n squared, that puts a kibosh to it. So, all right, so you write out the whole expression, absolute value, don't forget that. The whole expression with n replaced by n plus 1 throughout. So I have n plus 1 squared down below. We're going to have 2 n plus 1. And then you write the original expression flips. So I have n squared 2 to the n over minus 1 to the n, minus 1 to the n. Okay. So what you can do, you have different expressions above and below. Take similar expressions and line them up under each other. Single fraction. So for instance, minus 1 to the n plus 1 over minus 1 to the n, x minus 1 to the n plus 1, or x minus 1 to the n. Then you'll have n squared over n plus 1 squared, then 2 to the n, to the n plus one. So let's line everything up. Taking absolute value, so this. That's just one. If you have a polynomial in your original power series expression, you can have a polynomial evaluated n, and also that same polynomial evaluated n plus one. That's always going to go to one. So this sort of expression will never impact the radius of convergence. Whatever you have here involving x will always simplify to x minus the center, whatever that center is. The interesting part of it comes from any exponential functions, or if you have actually, or factorials. This example doesn't have factorials, but those are the kind of things that actually have an impact. So what ends up happening is you're always going to have in your limits, you'll always have x minus the center. And then this simplifies in this case to 1/2. So you end up with that for a limit. So it's a matter of sorting out what actually contributes to the limit and what doesn't, because a lot of things don't have an impact at all. But you'll always have x minus the center in the numerator. And then any exponential functions or factorials will show up in your limit, just a matter of where. The question is about how the limit was worked out. For convergence, you want this to be less than one. Rearrange it so that you have absolute value of x minus the center less than something. That something is your r. Yes.
So, minus one and plus one, raise to the n plus one over minus one and. Oh, wait. No.
It's minus one, but then you're taking absolute value of that. Yeah, don't forget the absolute value. That's containing everything.
Okay.
Question before I do the interval. Okay. So our endpoints. That's when the absolute value of x minus one is equal to the radius. So it means that x is equal to 3 and also equal to minus 1.
Then plug in.
Yes. So first you check, so you set x equal to one of your endpoints and you plug that into the original series. And it'll simplify quite a bit. To have minus 1 to the n, minus 1 to the n over n squared 2 to the n. Well, here I have minus 1 times to the n, and then minus 2 to the n. So here I have minus 1 to the n times minus 2 to the n. This whole thing here equals 2 to the n, which cancels with the 2 to the n down below. So everything cancels almost, and you're left with 1 over n squared.
One more time.
Right. So I plug in x equal minus 1.
Okay.
Now, so this is minus 2 to the n.
Okay.
But here I have something to the n times something else to the n. I can multiply those bases.
Oh. That's what then it's true to the end.
Yeah, which cancels with the other 2 to the n. Yes. It's P series where P is greater than 1. So it converges at that endpoint. Whereas if I had an n rather than an n squared, it would diverge there. So whatever power of n you have somewhere in this expression will never affect the radius, but it will most definitely affect whatever converges at an endpoint. Questions about this endpoint before we look at the other one? X equals 3. So now you have minus 1 to the n times 3 minus 1 to the n squared 2 to the n. So this right here, that's 2 to the n. That cancels with the 2 to the n down below. So what you're left with is minus 1 to the n over n squared, but we just saw that the series you get from the absolute value of that converges. This by alternating series certainly converges. So it converges at both endpoints. So the interval of convergence is, you can write it in different ways. So from minus 1 to 3 with the square brackets, not parentheses, square brackets, because the endpoints must be included in the integral convergence. Or you can write it this way: minus 1 less than or equal to x less than or equal to 3.
Oh, so for this, we're never gonna have parentheses
Oh,
in our interval.
it can happen.
Yeah.
Yeah, because one of these diverged. Yeah, if I change this problem to have just n instead of n squared,
It's diverged.
yeah, then I would have a parenthesis here.
Okay.
Yeah, so you can have either, both, or neither endpoint. Anything's possible. Yes.
Okay.
So if the absolute value of an alternating series converges, then the alternating series always converges.
Yeah, it would. Yeah, so the absolute convergence in reverse.
This absolutely converges.
And when you plug in the endpoints, generally what's going to happen is the two series you get are very similar, but one of them's going to have a sign flipping and the other isn't.
Yeah, that's why I asked. They're mostly gonna be the same thing.
It is, yeah. So then it matters that like, sometimes what can happen, maybe what you get is a geometric series with plus or minus r. But when it's a geometric series, when you get at the endpoints, that tends to be both endpoints diverging. Because then your r is plus or minus 1. When you have a n squared, a power of n greater than 1, that tends to lead to both endpoints converging. If you just have n in the denominator, then you have one endpoint converging, the other not. These are things that tend to happen. Check it out for yourself when it deals with real problems. But okay. All right. A lot has been said about power series,
Yay.
expectedly. But we still have some time to talk about any other problems.
Do you have any old midterm practice exams, just so we can do, if we want to do like extra problem?
I can check among my files. I'll just make sure that isn't something that I have to be giving on the real test.
But
But if I find something distinct, I'll put it out there.
thank you.
Is there actually gonna be a question where we have to approximate the sum or the error?
Okay. Let me make sure.
Like number one?
Okay. I have it on number 9 as a bonus.
But that's it, it's just
Yeah.
a Z bonus.
Yeah. Yeah, but the real question is just, does the series converge or not?
We just gave them.
Oh, okay. Oh, you mean you talking about the 4 points for free? Oh, no, that's something else. Okay, to explain what was asked about. Because there are 12 problems in a test, I'd like to have each problem worth the same number of points. But 100 is not divisible by 12. So I just made each problem worth 8. And then, so if you do nothing at all, you'll have a score of 4.
It's not bad.
No one's gonna get a 0. But then, if you do the bonus, that's a chance to get a number 8. Yeah, I want to try to encourage people to
Double
try
my
it.
score.
So the highest possible score you can get is a 108.
There you go.
Can we work out the approximation for number 9 then?
Oh, for this practice test?
Yeah.
Okay. Well,
So if we, okay, this is stupid, gonna sound stupid, but if we write something down and explain what we thought and it's completely wrong, how many points, would I get like 1 point or 0 points?
okay,
But you tried it.
I tend to only give 0 points if it's either left blank or there's so little written down that it can't even be construed as an honest effort. That's when you get actual 0. Like, okay, with each problem worth 8, if you seem to generally know what you're doing, but you mess it up somewhere along the way, like a minor, like an algebraic mistake, then I can give you a 6. And then it just goes down from there. But if you show me that you know something, that's how you can get some partial credit. If a problem's asking for more than one thing, then you're gonna break the points down accordingly. Like, for example, for the power series one, the number 12, it asks for the series and a radius of convergence. So I can divvy up the 8 points among those 2 tasks.
Okay.
So obviously getting a power series takes more work, but okay. So there's no one thing on this test that if you can do too much damage to your grade. If you end up just throwing up your hands and then you get blank. Okay. Oh, you want to look at number 9? Okay. For God's sake. Okay. I hurry, but no one will understand.
Working the clock. JK, I'll wait after.
You do like an all night live stream. Let's go through the problem.
Mathematical version of a filibuster.
Yes.
Alright, so here I'm telling you the series converges. It didn't make much sense to put on a bonus about approximating it for my diverge. Okay, but for this alternating series test, it's enough. Actually, so because not every test leads to a way to find out what the value of the series or the approximate value is, but the alternating series test does. So if I let S be the sum of the entire series, okay, and then I have, I'll let the SK do sum n equals 1k of the same thing. Then the alternating series estimation theorem states that the absolute value of the true sum minus the partial sum is less than or equal to the n plus first term, so. Okay, sorry, I've not explained my notation here. In this case. BK is what you're summing except for the sign flipping part. So. The remainder. Is, so the error is less or equal to the next term. So it's a good way to think about it. The next term in absolute value. Okay. So think of it that way. So in this case, you want to find out how many terms do you need to be within 0.001. So we want x minus fk less or equal to 0.001. What? Okay. So you replace this with the next term. So instead of k, you have k plus 1. So 1 over 1 plus square root of k plus 1. All right. And then you solve this inequality for k. And that's how many terms you'll need to include in your partial sum. So to carry out the algebra, you cross multiply. So 1 over 0.001 plus 1 plus square root of k plus 1. But 1 over 0.001, that's 1,000. Okay, so that means square root of k plus 1 is greater or equal to 999. Yikes. So you solve for k and okay, so you're gonna need a lot of terms. Now, to help you with a sanity check for whatever answer you get when you work this out. The reason why so many terms are needed is because we have n raised to the 1/2 power of error. So this fraction, it does go to 0, but it goes to 0 really, really, really slowly. The larger the power of n that appears in the denominator, the fewer terms you'll need because it goes 0 faster. So, so if you get some obnoxiously large number, when you look at your power of n, it's like, oh, that's a slow decaying function, but that makes sense.
So if it were n factorial, then we wouldn't have a very large number, for example.
Not at all, yeah.
Yeah.
But of course, that's also difficult to solve for the algebra. In some cases, all you do is trial and error. Just because of what you get here. Like this one can be worked out. Now I gotta see what I put in a real test.
Here, let me take a look.
Funny. Okay, I will simply say that the algebraic complexity will be similar to what you saw here.
So I mean, this is silly, but I forget when our sign splits.
Oh, wait.
What, I forget what, we do when our, like, to make our sign split.
Oh, a minus 1 to the n. So multiply by that.
No, I'm in the. What is this called? Inequality sign.
Oh, okay. If you multiply both sides by a negative number, the direction of the inequality will flip. But yeah, that's something that didn't come up here. Here I subtracted, but that's not gonna change it. It's only multiplying by negative number. I actually found that the root cause of most mistakes that you think in these kind of classes are mixing up properties of multiplication and addition.
Yeah.
Yeah, it's silly mistakes like that.
Yeah.
Okay,
Okay.
Yeah.
There's still 2 minutes.
I have another question.
Okay,
So this one's quick.
we'll go to 2 minutes.
Yeah. So Can I write it on the board?
Okay,
I'm gonna write it right here. So. Um. Okay. My question is, how would I go about without solving it?
that series does not go to converge.
Yeah, it's false.
Oh, okay. That's false. That's
Yeah.
reassuring.
It's
Um,
false.
Okay, the key is the power, the highest power of n in your fraction, because here, you have this sequence going to 0 because you have the denominator's function of n that goes on to infinity, and the numerator is just 1. But, you look, when you have a situation like this, look at the highest power of n, or if you had a more complicated expression of time, you look at the difference of the powers of n. Because you can wait to show that this converges or diverges. Best way to do it is limit comparison test. You figure out what is the power to compare to. In this case, it's going to be 1 over n.
Which does diverge.
Yeah. So yes, that's how you would like conclusively prove that it does. But on a test, you can just say like, oh, well, this is similar behavior to 1 over n, which diverges during this divergence.
Okay.
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 Was my last?
I don't mean to be rude. I just gotta get all the way across the.
Oh, yeah. Okay.
I'm sorry. Sir, I sent in the ODA.
I filled it out.